They are taller than the ceiling here, so more than 6 meters tall. And you have to imagine we have then sometimes 10 or 20 of these battery packs on such a vehicle. Monster type of application, so it's at least 10 to 20 times more powerful than a car. So today we are in Baden, in Switzerland. This is the place where we started actually producing batteries 6 to 7 years ago. We do everything up to the size of this component here. This is something we call a battery pack. So in this specific one, I mean, you have to imagine that the cells are arranged like this, yeah? So over these 2 stories of cells, we have more than 500 of these units in, yeah? And then many of these, sometimes 5, sometimes 10, sometimes 20, go then on a large vehicle. And then they are there to propel the vehicle forward. What we see here in the back, this is the assembly line for kind of a building block of the battery pack. We call it battery module. We put the cells together, we do a laser welding, so we connect the cells among each other. And then what the person in the back is doing is the final assembly of the modules. So we will put some electronics on top to measure cell voltages and currents. Again, very important for safety purposes. Then we assemble it, and then we do a testing line. There are 2 measures, or actually 3 measures that are important. First is the energy content. We measure that in kilowatt hours. So the people that have an EV at home, sometimes they have 20 kilowatt hours, sometimes 50, sometimes 80. This gives you the range. That's one important parameter. The second one is how quickly you can charge and discharge. Very important parameter. These batteries are special in that they can be charged very quickly. There is a parameter which is called C-rate. So C-rate is compared to 1 hour charge-discharge, how quickly you do. So C-rate of 1 would mean you charge in 1 hour, fully. So this is what a car battery normal has, 1 to 2 C max. On this ones we can go to 8 or 10 C. So for short durations of time, we can charge them theoretically in 6 minutes. Normally you don't do that, huh? But that's kind of to give you the order of magnitude. So 5 to 10 times faster than the car battery. Yeah? And the third part, which is very important, is how many cycles they can do. So the life of the battery. These again are for very demanding applications. So they can do 20,000 cycles, 40,000 cycles, compared to the 2,000 to 3,000 that you have on your car. So it's a different breed of battery actually we are producing here. Yeah? What we see here is a special design that we use for special vehicles. So when the vehicle has a very special mounting space, we can actually also, adapt the shape exactly to the mounting space. You see this shape here is basically just the frame of the vehicle. So we have now actually the capability to deliver the standard components or to design the battery exactly to the shape on the vehicle.
What kind of vehicle is this one for?
This is a railway maintenance vehicle. So to do maintenance of the railroad tracks. These cells, you can think about them as a small chemical reactor. Okay, so inside here you have a plus pole, you have a minus pole, and they are connected to an aluminum sheet which is coated with materials. These materials, they really make the performance parameters of the cell. Okay, so then the cell manufacturers, they can tune these materials, they can tune their manufacturing process, and they will get a certain result. Okay. So in the car battery, you have NMC, which is tuned for energy density. So there the focus of the cell manufacturer is to have range, okay? But they need to compromise on cycle life. So it's the battery ideal for a car, okay? In this ABB product here, we have LTO, which is an anode material, so a minus pole material. This one is tuned for cycle life, okay? So that's the main property. So you have to imagine, if you take a car battery, this gives you 100 kilometers. With LTO, this gives you 100 kilometers. So the downside of this very long cycle life is range. Now here we are talking large mining vehicles, we are talking locomotives, we are talking passenger trains. So then LTO is, in our view, the technology that matches the application and has a benefit that comes on top of this range versus lifetime I just explained, and this is safety and robustness. So by the very design of these cells, they are not prone to thermal runaway. So a fire with these batteries is extremely unlikely. And the second thing, they are robust. So you can leave them in the sun, 60 degrees, 70 degrees, you will be able to use them after that. If you do that with NMC, it will suffer a lot. So even this LTO technology that we are currently having is going to increase in energy density. So this is an ongoing process. Cycle time is maybe 3 to 5 years, and then you have 10% more in energy density. Okay? So this is more an incremental step. Then there are completely new materials that are being analyzed, like niobium-based technologies. There is also this sodium ion-based technologies. And again, we screen them early. We try to track what's going on, and as soon as they are ready for one of our applications, then we will also package them. And it's really continuing as scale grows. You know, the market grows, manufacturers ramp up their volumes, things just get better, and we fully kind of follow this curve of improvement. Yeah.